Lincoln Parish Park in Ruston, Louisiana is planning to add a structural steel bridge to their disc golf course to span water features. Students were challenged with developing a 1 to 10 scale bridge design for consideration. This year, Olivet Nazarene University's team is composed of 6 student members and faculty advisor Professor Scott Reagan. The past academic year has been used to design, load test, estimate costs, and fabricate the potential bridge model. Let's take a look at Olivet's proposed design.
There were several things to consider while developing a bridge design. Construction speed, lightness, aesthetics, and ensuring the bridge design can hold the intended load with minimal deflection were all considered while designs were created. We have decided to use a simple Pratt truss for our overall design for a multitude of reasons. First, a Pratt truss's bracing members act entirely in tension. This allowed us to use flat plate steel bar for all of these members. Secondly, a Pratt truss's vertical members act in compression. This led our group to design these sections out of steel angle. Steel angle works very well for creating flush sections between our members. Lastly, a Pratt truss is simple to construct. This will be discussed more later. Our model features thicker angle steel for the top cords or stringers to bear the initial load on the bridge. These members' thicknesses were created to produce minimal deflection in the stringers. Our model also featured X bracing at the intersections of all horizontal members. This design produces minimal sway when our bridge is subjected to horizontal load. These bracing members were also created using flat plate steel bar because they act strictly in tension. ASTM 36 steel was selected for all members due to its availability and inexpensiveness. Grade 8 half-inch diameter bolts were selected to achieve connections between all members. These durable bolts were chosen due to their high strength under a multitude of load scenarios. Let's now look at the analysis of our model.
Olivet ensured that the bridge model was analyzed both through structural loading software, but also on the physical bridge. Visual analysis was used because of its customizable design features and inexpensiveness. Through visual analysis, we were able to easily manipulate the dimensions of members, type of steel, and dictate which moments were released and fixed for correct analysis. We received a reading that our overall model deflected around 0.165 inches vertically, while under 2,500 pounds of vertical load. These numbers were based on load case number 3. Because things always work differently in the real world, we decided to physically load our model to measure deflections. We used 56 45-pound plates placed on wooden pallets to load our physical bridge. The maximum vertical deflection measured from the top stringers was 2.1 inches under load test 3. Additionally, we tested the horizontal load. We used a hanging scale and pulled laterally on the bridge in the center of L1 for load case 3. This produced a sway of less than 3/4 inches. Load case 3 produced the largest deflections for our bridge compared to any of the other load cases. We'll next discuss the fabrication of our bridge.
Olivet ordered all steel material from Belson Steel in Kankakee, Illinois. This steel fabricator used recycled steel for all their material. All steel was delivered in 20-foot sections. Our students cut all members to their desired lengths using a combination between miter and bandsaws. Next, holes were punched for all bolted connections. This was done through an automatic drill press on a hydraulic iron worker. All holes were punched to a 9/16 inch diameter to meet AISC steel manual code for bolt hole clearances. Student members also grinded down all steel members and punched holes using handheld angle grinders. Welding was achieved with the help of a local welding shop. Shear welds were created between sections of members to maximize the strength of our vertical steel angle. Our model was also painted to match the school's colors. Purple was used for all vertical and horizontal members, while yellow was used to signify all bracing members. A 50-watt EMP fiber laser was used to engrave all members of their location on the bridge. It was also used to label the school's name. Once our model was fabricated, it was then time to begin to practice for time construction.
Time construction was one of the primary considerations while developing the design for the park's new bridge. Our model is simple, with few intricate sections to allow for easier construction. Our group uses 6 members for construction. This includes the use of 2 barges. Our team completed the construction in around 25 minutes. Minimal tools were required during construction, including impact drills and wrenches. Olivet's design is unique to those also up for consideration. It is simple in its use of a Pratt truss. This allows for fast construction and easy connections between members. Its structural integrity is incomparable. The model meets all loading requirements while producing minimal deflections. And its inexpensiveness makes it easily affordable for the buyer. A36 steel is available everywhere and is easy to fabricate. Overall, this model meets all requirements laid out by the Lincoln Parish Park. Thank you.